Good evening, everyone. Thank you and welcome to our third computational AEC event. So we are already behind the schedule, so I'm going to first thank to Arup for giving us this awesome facility for tonight, and a few formalities that I have to go through. So first of all, Arup acknowledges the traditional owners of the land on which we meet, the Wurrung and Boon Wurrung peoples of the Kulin Nation, and pay our respects to elders past, present, and emerging. Emergency exits are on the Sky Park spiral stair. And the location of bathrooms are just behind the library over there. So without further ado, I just hand over to our presenters tonight. This works. Tonight we have John, Rhys, and Josh, all from Arup, sharing their knowledge and experience with us. So I'll welcome John. John is a senior structural technician and regional parametric leader for the infrastructure team at Arup. John was previously CAD leader for the building structures team in Melbourne for 20 years. Before joining the bridge and civil structure team in 2016. John has been using BIM and digital tools since the early 90s and parametric tools for the past 15 years. John played a lead role in the successful implementation and use of these tools and processes in the Melbourne office and across the region. Thanks and welcome, John.
Thank you. Thanks very much. First, I'd like to thank Giovanni and Hans for the opportunity and the committee, the opportunity to present today. It's kind of, when Giovanni asked me to share some stories about the history of these tools within Arup. Rhys and Josh are going to talk about some of the current tools that we're doing, what we're working on, as well as doing a bit of stargazing into the future and do some what-ifs. I was quite excited when Giovanni asked me to present because normally when I present to people about parametrics or computational tools, their eyes glaze over like you're talking about a medical term. They don't understand what you're talking about. So I'm hoping that I'm kind of preaching to an audience that gets it, understands it, and is enthusiastic and passionate about it. There's a couple of themes that will recur through the stories that I'm going to share with you tonight. One of them is that it's just a journey. I've been lucky. I've been in the industry. This is my 40th year in the industry. I've been at Arup 35 of those years. The bulk of it in the building structure space and recently in the infrastructure group space. I started on the drawing board, was in CAD in the early 80s, doing 3D CAD, BIM in the early 90s, BIM in the late 90s, Parametric in the mid 90s. I've seen a lot of transitions through my career. And I dare say that in your own careers, you'll see the same sorts of transitions. So if there's one theme that I'd like you to get out of it, is that the tools will change, the way you go about what you do will change, and the rate of change is accelerating compared to the 40 years that I've spent in the industry. You can see that already. The other theme is that I'm a big believer in, you call it BIM, digital twins, whatever it is. For me, it's all project delivery. We deliver projects. The tool, how you go about it, is semi-irrelevant. But I'm a big believer in what they call human-machine symbiosis. Human plus machine is always more powerful than human on its own or machine on its own. It's a combination of the two. the creativity thinking of the person, put it with the knowledge and the power of the tools that you're working with to deliver the projects of what you're doing. The other thing is, every project that I'll share with you, there's no such thing as rainy days in our business. You're either busy with projects or you're not busy with projects. Every project is an opportunity to use a new tool or to test something out. Each project that I'm going to share with you today, that's exactly what happened. They didn't go around and play with it and then use it on a project once they proved it. They were using these tools to actually help deliver a project. And that's the key message, because I see a lot of people waiting for that rainy day before they invest in it. Every project is an opportunity to test, play and explore, and I strongly encourage you to do it. And the last one is the why. Why do we use these tools? We use these tools because design, what we do as designers, is an iterative process. I kind of liken it, we start out here with a concept, we fine-tune it, we fine-tune it, we fine-tune it, we fine-tune it, and we go, Mr. Contractor, go build that. So these tools allow us to deal with that iteration in a lot more easier way than in the drawing board. I normally do a presentation with a young bloke who does a live demonstration of the tools that we're using, Grasshopper and Tekla, and he gets just frustrated if they don't update within seconds. And I kind of go, Aidan, cut yourself some slack, try doing that on the drawing board. Take you hours. The other thing that I'd like to, you should have made that red, right? Arup was founded by an engineer who was also a philosopher, Arup. He had a couple of visions, or a couple of key criteria. One of them was quality and integrity, and also delivering projects. So that's the core. These tools allow us to deliver products that have better quality, more integrity, but more than that, I believed in what he called total design or total architecture. And he wasn't really referring to architecture as such, he was referring to the whole design process. And what he meant was that good design means that something is easy to build and can be built. We can all do calcs, and we can, you can make anything stand up, but that doesn't mean that's a good design. So OVE was all about an holistic approach that was involved the architects, the engineers, all the engineering disciplines, and every other discipline to deliver a product that is best result. And that's what we're trying to strive for. So I'm going to share with some stories about some projects that we've done over the years. So the first project that brought Arup is a global firm, started in the UK 50 odd years ago. The first project that brought Arup to Australia was the Sydney Opera House. This is also one of the first projects that they used digital tools. Competition was won in the late 50s and designed through the 60s. It was to do the calculations and deliver the project. They engaged a company and that was using these mainframe computers. They also wrote specific code to enable them to do the calculations. That's the beginning of Arup had their own internal software company called Oasis, which developed some analysis tools. And this is the starting, or the kickstart for that relationship, or that part of the industry that we had. So they saw, back then, in the early 60s, saw the vision of taking advantage of the power of the computer to help deliver the Sydney Opera House. And there's a slide up there of the wind bomb testing that's done. I'm going to talk about some. The projects I'm going to talk about are mostly what I consider milestone projects. I can't, there's not enough time to talk about every project that we've done, but I do want to talk about, kind of give you an idea of the journey that we are, because I'm a big believer, if you don't know where you've come from, you don't know where you're going. So, this was one of the first projects that we did a 3D model on. For those that are not my vintage, the why, I'll go back to try and explain the why in every project. When this entrance canopy was being designed, this concrete frame building already existed. It was already built. This is a cantilever structure. It's got a backspan truss that had to pull back in between all the existing columns and be tied to the roof. We had to build a model of that, and then pass it through to analysis to make sure that the geometry fit. And that was the beginning of our journey using 3D tools, and that was in around 94. Then the National Museum of Australia is one of my favourite projects. One reason being I grew up in Canberra, so this is an iconic project on a very prominent site in Canberra itself. It was also the first project we used when the architect was using Rhino. It was also another milestone project because in those days a lot of architects did 3D models, but they did 2D CAD files. And at some point the models separated from the CAD files, so just use the models for regular. This is the very first project when we flagged with them your CAD plan or your elevation doesn't match your model. The architects came back and said the model is correct, we'll update the drawings. This was designed by ARM. And again, for the same reason, the why. Why did we do a 3D model? It's very complicated geometry. We had to cut slices through the model, produce where the structural columns and beams and trusses need to go. And then again, we pass that on to analysis tools to do analysis with. And that's a common theme that we've used on many of our projects, and you'll see that it's all about building a model, going to analysis, and then coming back and doing the documentation. In the late 90s, Bentley released a tool called Triformer, which is now called EcoSim. It allowed us to do a BIM model. The same thing that we do today, add data to your attributes, place a beam, column, or wall, etc., etc., etc. Do your reports, blah, blah, blah. It was done in the late 90s. This is a two-storey building, educational building for Victorian University of Technology. We broke even on this project, proved to be a success, and we've basically been modelling every structure in this office ever since. Then I'll roll on to the MCG. The MCG was, I consider a milestone project because we're one of the few disciplines, or the only discipline actually, that used the model to generate the drawings from. But more importantly, this was the first project where we started modelling the silhouette connections. And again, if I come back to why we do what we do, if a picture tells 1,000 words, what's the value of a model? At the end of the day, we're in the, it dawned on me ages ago, that we're in the communication industry. We like to think we're in the design industry, we are, but essentially we're in the communication industry. We've got to communicate to someone, either our other design team members, or the client, or the contractor, what it is we want them to do. And a model is the best way of doing that, and especially now that we can add a lot of data in those models. So this is the first one, that's the roof node at the bottom. You can see it in the fabrication yard and then out on the side. And then in the UK, around the same time in the UK, so this is the late 90s, early 2000s, this is the first time computational design was being used within Arup or within our experience. This was done with Foster's, so the next two projects were done with Foster's. They built a script in MicroStation to generate the geometry. So it's not parametric as we know it today, it's not the parametric tools where you're building a relationship model and you can update it. This is a script that they run, and if you want to generate it again, you wipe the other one and then rerun it. But it generates the same sort of thing. The other thing that Arup did at that time was we built a Tekla model of that job. So Tekla is a fabrication software. What that allowed us to do is it allowed us to deliver the project early, detail the connections and communicate that with the fabricator. This was done 20 years ago. We're still chasing this in what we're doing today. The next project is around the same time with City Hall. It's done around the same methodology. The scripting was done using by Foster's architects, same processes that I was doing before, and then we produced a Tekla model within Arup with the same reasons. Again, back to the why. Then in the early around 2003, the next two projects are around the Beijing Olympic Games. We were lucky in that Arup won quite a few of those games. This is done with Sol de Moron, if I pronounce that correctly. This is our first project that I'm aware of that we've used a parametric tool. And the parametric tool used on this project is CATIA. CATIA is a product that's been around since the early 90s, developed by Dassault. It's used by the aerospace industry, mechanical and other such things. It's a very powerful tool. And also at the same time, there was a guy at Arup who's unfortunately no longer with us, Jay Parrish. He was a sports architect. He spent most of the 90s and early 90s writing code to generate the optimal design for the stadium bowl seating. Because basically every stadium is set around the bowl. What your sight lines, what your distances, what your viewing angles are. That's pretty much defines the criteria for a bowl. So Jay Parrish wrote a lot of scripts and coding before he then went into the parametric tools to be able to regenerate bowl seating arrangements, 50,000, 60,000, all that sort of optioneering. Then the roof structure itself, as I mentioned, was all done in CAD. It's quite busy, but really it's a fairly simple project. These are portal frame trusses, and then the rest of it is just placed there so that no one can read what the structure's doing. Why was CAD used? So the geometry was, to play around with all the things we do today, play around with all the optioneering. There's an next slide I'll talk about a bit more. Basically, the roof itself is a torus. The advantage of a torus, which is basically a donut, is that it's a radius in both directions. So the geometry is quite uniform. And the plan view show itself is part of the leads. CAD, because CAD is used in the mechanical industry, you can generate your geometry and then create true or developed shapes, which is what they did. So they produced the drawings out of CAD, and they could generate the true envelope of the steel plates. They did a lot of prototyping with the welded connections there. You can see that there. They proved that it worked. Once they were satisfied with it, then they ran with it through the job. And again, the same challenges that we have today is that these tools at that time allowed them to play around with all those options. The water cube. The water cube was done by a Sydney office by Steve Downing and his crew up there, for those who know. Again, this competition, this was done with PTW in Sydney, and they won the competition in 2003. The geometry behind it is quite clever. Soap bubbles or bubbles is quite a strong structural form. They took the concept of bubbles within a foam environment, and they had they cut it at an angle, a slice through it. Then they had two skins, one for the outer skin, one for the inner skin, and then the bubble lining itself is made out of ETFE, and it was pumped with air. So it was actually a way of creating a structural frame, both inner and outer, but also acted as the insulation for the heating and cooling of the building. You can kind of see there, it was early days, back in those days, but they created a 3D printed model, and then you can see our potential, quite a lot of the model there. Very impressive. Now the workflow, again, this is a milestone project for us because they did a lot of coding. All this was done in MicroStation. They linked it to analysis, and then they brought the analysis data back into a MicroStation model, which they automatically generated the drawings on. What this allowed them to do was quickly turn around a lot of different options. Again, it's not a parametric model in that it's linked, but it's done through scripting. So you clean the model, redo the script, create your drawings, look at your options. So you can kind of get a sense for what it's doing. The optimization routine that they developed for this, so an optimization routine is where it's an iterative process that runs through all the members to try and refine the design down to as optimal as possible. This optimization routine that was developed here is now still being used and is being rolled out into a lot of the projects that I'm going to show you after this. So again, I'm trying to emphasise that where we are today is on the back of what was done before. We just keep refining and improving it. That's some slides and scripts. It's also, again, the value of having the data or the model. You can pull that data out and start doing some testing and studying on it. Some examples of some drawings, just some images of the project. on the site. The next one, so this is Marina Bay Bridge, double helix bridge, done out of the Sydney office again by Steve Downing and his team. This is the first project that we use a proper what I call a parametric tool here in Australia. It was done using Bentley GC, which was released about 2004. This is a double helix bridge, but effectively it's designed as a tube. A lot of the optioneering was done in CATIA, form finding. Then when it was rolled out to project delivery, it was delivered using Bentley GC. GC is there's an image on the right there of the GC noding, which is those that are familiar with Grasshopper. It is a very similar sort of context. I think the best description I think of these graphical or visual programming tools is your relationship modelling. You're building a model that has a relationship between 2 points, which when you connect them, it could be a beam or a column. Geometry starts to become irrelevant. Where the X and Y and Z is kind of, you can plug in later, but you're just capturing that relationship between all those objects. And then when you build on that, and you build on that, and build on that, you get the powerful tools that we've got today. Just some images of the different geometry options that they explored, and then the model that was used for documentation. Same sort of concept, and again, this is done back in 2004. 3D steelwork connections, as you can see. And then, like today, take data out of the model, start doing reports, doing your comparisons, blah, blah, blah. All the stuff that we kind of take for granted. Amy Park, I'm a sports tragic, so I've been lucky enough to work on a lot of stadium projects. I also played rugby as a kid, so big fan of this project. It's the first project we did here in Melbourne using GC. Again, the early concept work was done by Dominic Holzer, for those in the industries at Melbourne Uni. He was a PhD student with us at the time. He did a lot of the concept and form finding, working with Tristram Carfrae in Sydney. When it came to project delivery, we brought it into GC, built a parametric model for 2 reasons. Why? We wanted to run some optimization studies for the geometry, but mainly we also wanted to allow the ability to, all steelwork structures have a pre-camber. Every node is connected to another node, so when we wanted to raise the lip of the roof to hand over to the fabricator to do their steelwork shop drawings from, we wanted the ability to raise that roof quite quickly. So we built the script that allowed us to do that. Some examples for those that haven't seen parametric tools used, I've just done some exaggerated slides of playing around with the different geometry. So you've got the shell raising, the individual shells being raised, and then a combination of both. Having that allowed us to run all those different options, spit out a text file, which we could then map. We had a programmer map to the analysis tool, so we could spit out 18 different geometry combinations in minutes, and then the analysis would run overnight. We'd make a comparison of those things, and then run another case study of the best combination of both. So that's an image of the analysis model, and then this is the Bentley model that we use for documentation. Same thing. And then we handed over the preset model, gave it to the contractor and the fabricator to start working from. The next milestone project is Marina Bay Sands. This was done in conjunction with Moss Safety Architects. It was one of our first global projects. It was 3 50-story towers, convention centre, theatre, art science museum. A lot of the optioneering was done parametrically and done here in Melbourne. When it came to detailed design, it was done out of the Hong Kong office, the Singapore office, of course, and the Art Science Museum was taken to construction here. I'll go back to this model. I still say to most people, if someone walked in today and said, can you do this today and do all that fabrication accurate model, to give over to the contractor. I kind of go, holy hell, how am I going to do that? And this was delivered back in 2007. All the steelwork on this project was handed over to the contractor for the fabricator to just finish and do the shop drawings. All the geometry was set out in our models. And the main reason, if I go back to the why, was this project. The Art Science Museum, which we did here, was fully parametric. Again, a couple of reasons why. We had to, imagine trying to do a set-out drawing or convey that information to the shop detailer. Can you go build this model if you don't give them a model? It wasn't possible. When we started this project, just some more images. Basically, that's a 10-story high from the base of the diagram to the palm of the lotus. So it's 60 metres in the air, or 30 metres in the air. This was the concept we were given when we started this job. We were not banana. But Jim Pay, who's, for those in the office, Jim Pay is a guy I worked with for a long time. This is one of his first jobs. He had oranges like and a banana, and he decided that the lotus looked like that. This was the sketch that we started with. We had 3 months to go from that sketch to a full model, design analysis, and go to tender. And then we had another 3 months to refine that model and then hand it over to the fabricator and say, go build this. Quite a challenging thing. We built a federated, back in the day, GC, and Bentley GC's, it was 2 meg of RAM, could run on, and then it would crash. So we basically had to do the whole thing in a federated scripts, essentially. So we had a script to define the primary geometry, then a script to do each finger, then a script to do the diagram, and then etc., etc., etc. The beauty of the scripts, as you hopefully all know, is you write a bit of code or you write a script, you prove the logic for one, and then you can reapply it on the 10 fingers or the top of the model surfaces or whatever. So it's quite repeatable. The architect developed all their geometry, they did everything in Rhino, even all the drawings. It's probably the most perfect Rhino model I've ever seen. Had the tiles in there, finishes, handrails, the whole caboodle. Very proud of this job. This is some images of the federated scripts and then the combined model. Some images of the architect's model, the analysis model, the Bentley model, and then some of the drawings. The iteration, obviously, we went through a lot of design iterations with this project. And then what we did was we went from Bentley over to Tekla, handed over a Tekla model. The beauty of that, and we've still come back to that thing today, the beauty of handing over a Tekla model to the contractor is that when we get their model back, we can easily run comparisons. And it saves in shop drawing time, saves in review time, etc. So there's huge advantage in that, and that's something that we're still chasing today. Some examples of the construction and the final product. Now I'll talk about a couple of other projects. So this is Alba HQ at Dubai. Similar sort of workflow, going into 2008. GC model to define the overall geometry, take it to analysis, from analysis to a Bentley model, from the Bentley model to a Tekla model. Tekla had model handed over to the fabricator with connections. And the facade for this project was done in CAD. And then that's 12 years ago. Just some examples, some of the drawings, some of the Tekla model. Same logic as Art Science Museum, being able to compare the model with the model you get from the shop detail. This is the Ice House in Melbourne. A milestone project for us because this was, I talked about the National Museum of Australia. It was 10 years before I there. This was the first project that I worked on where everyone worked in a model and the model was true. So the architects were using Revit, our MEP team were using Revit, and we did everything in EcoSim. We built a parametric model because we had to go from The project was awarded in November 08, and then it had to be delivered in 15 months' time. We had to start design and hand over a model to the shop detailer so they could work on it over Christmas, so they could put poles in the ground and erect the columns in March. So when we started this, we didn't know what the truss framing arrangement was, what the column sizes were, any of that information. It was early days. So again, we worked on a relationship model, we built that relationship, and then when we've got that data, we're able to put that into the model and turn it around. This was also the first time that we're able to model. The tools allowed us to model the objects, beams, columns, walls, using the parametric tool. Previous to that, we were running scripts through in-house. We'd written code to be able to pass from one tool to the other. Then I'll roll into Adelaide Oval. Again, I'll talk about milestone projects. This was done with Cox Architects. So you can see, hopefully, a lot of that early work was done with CATIA and Bentley GC. Grasshopper was released around 2007, 2008. Architects started using it. Our engineers started using it more. Engineers take to Grasshopper like ducks to water. This was also, as I said, the time when the architects were using it. So Clayton's here, he worked on the project. So Cox Architects did the parametric model with our input. Stuart and Greg, not Stuart, Clayton and Greg at the time, provided that input with so it was done collaborative with the architect. And then when it was ready to be used, we pushed it into the structural models. Just some slides of the two rooms. Again, all of them done parametrically. Some examples of the, just some of the drawings and the fabrication. The other thing I wanted to mention, all those optimisation from the water cube went through through Amy Park, and then onto Adelaide Oval, was reused on Adelaide Oval. Just some more examples of the mould, the drawings, and the fabrication. I'm going to talk about the Sports Hub. Sports Hub, so this is the last kind of old project that I'm going to talk about. The Sports Hub was done using digital projects. So digital projects was developed by Gary Technology, which is obviously part of Gary's architectural practice. It's based on CATIA. So it's an engine that runs on CATIA. Arup have used it on a lot of projects, Sports Hub being one of them. So again, similar sort of workflow, parametric model, take it to analysis, from analysis to a technical model. Just some more images of the slide showing the workflow. And then we did a lot of studies with rationalisation of the connections and also the member sizes. And again, that same optimization tool was run through here. And again, this is something that we're still chasing today, and hopefully, Rhys and Josh might talk about that. Just some more examples of the analysis for the connections. And this is a slide showing the GSA tech building. So again, if I come back to early days of the Sydney Opera House, what we, Arup, recognised a long time ago is that there's always a lot of gaps when you're moving from one software tool to another. So that's where we've taken advantage of programmers or coders or people that know how to push data, because essentially you're just pushing data from one place to another. So I'm going to skip all the projects that were done recently to that because they're kind of a very similar theme, I guess. What about linear infrastructure? What I think a lot of people, especially in Arup, forget is that the first project that was done, the Double Helix Bridge in Marina Bay Sands, in Singapore, was the first project we did using parametric tool. 2008, this bridge in Brisbane was designed by Ken Enright. Again, it's a bit like the Bird's Nest Stadium. It's more complex than it looks. This is actually a cable stay structure. It's got a canopy that's a 10-secondary structure, and the combination of the two makes it look a lot busier and more complex than the structural is. Again, why did they use a parametric model? Because they had to play around with the geometry of the masts and the cables to make sure that they got clearances and didn't clash, etc., etc. Again, passed to analysis. The next project I've shown this one because a lot of the projects I've shown, they're kind of stadiums or what you might call sexy projects. This is 2 kilometres of poled retaining walls done in 2010 for a project with John Holland, a grade separation project at Nunawading Station. We were able to, you build the script, you tie it to the rail alignment, you tie it to the existing ground. We didn't get the information from the geotech until one day before we actually issued drawings. It was an accelerated program. So you build the logic in the script first, then when you get the data, you push the data in, which allowed us to push out the models quite quickly and then generate the drawings and the schedules. This program ran ahead of schedule and was very successful. So I kind of try and push the message that these tools aren't just for your special projects, they're for every project that you use. You can take advantage of it. We did some tunnel studies for the airport link in Brisbane in the late 2008. From fast forward, got the Elizabeth Quay Bridge done by Clayton here in Perth, Grasshopper to Tekla, same sort of workflow, 2 analysis, Tekla, and then drawings. In recent years, I'm just going to talk about what we've been doing since the Georgia Bridge team, is Swan Street Bridge. This is my first bridge project, I guess. Obviously get a nice easy job to start with. It's got 76 steelwork fins each side of the bridge, 152 in total. The concept, the architectural concept is a little bit like oars in the water. Their length varies and their depth varies based on an algorithm that the architects came up with. We had to, the road geometry and the shared user path geometry kept changing, so we tied the geometry of the bridge and the fins to that geometry, so when we could deal with those iterations, we're also able to generate all the data that went to fabrication out of the model. It was also one of the first projects where we used a point cloud. Melbourne Water were quite insistent that the new arches that were put in match the profile of the existing arches that were removed on the outer edges of the bridge, of the original bridge. All the geometry on this bridge was done parametrically. All the set out information was extracted from those models. Probably something I haven't mentioned, if I go back to the why with Arup or with OVE, is it's all about delivering what we're doing. I'm not a big believer in spinning wheels for the sake of spinning wheels. We use these tools to be able to help us deliver a project. So in recent years, I've been on the Western Program Alliance for the last 18 months. We basically, in that time, been able to change how we go about what we do. We're now doing all of our bridges parametrically, generating all our drawings from the model and generating data from that model. We've delivered to detailed design 4 bridges so far. 2 have completed construction. 1 is under construction and 1 is about to start construction. Last year for us was a lot. I'll go back to, so this is the first project and the second one. And then, so these are completed. Just some slides. Why parametric? For the same reason that we did it in buildings, because we extract the drawings from it, we extract all the set out data. It helps us deal with the iterations that happen through the design process. The same logic that we do use in the building space. And it also gives us the ability to do a model from the start. The value of being able to create a model at the beginning as opposed to traditional methods is enormous. And the project team and the alliance are gaining from the benefit of that. So this is just an example of, as hopefully most of you know, week 1 it looked like that, 2, 3, 4, 5, 6. Went through many iterations in the early stages and then even through the detailed design stages. Last year was a lot of options for us. We were able to turn around probably 30 odd different bridge options on 6 or 7 different projects. We're about to start detailed design, or we are in the middle of detailed design, about 6 or 7 structures. So by the end of the year, a lot of these structures will be built. Again, the same logic for why we do something parametrically. You build a bit of code, you write a script, you build a parametric model, you can reuse it, tweak it a little bit over and over again. So we're able to generate a lot of these options quite quickly. And I'm looking forward to taking these to detailed design and 3D construction. This bridge, the bridge that I was talking about, this is under construction. This was also 3D reinforcement models we've been exploring. I'll talk about that later. Just an example, the culverts. We also took these same, I'll just show some more bridges that we did. Options. The rest of the rail infrastructure, we're using the same tools for doing our overheads, our gantries. Build a component, run it through a script, go place it, bang, 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 bang. It doesn't matter whether it's 1 kilometre long or 20 kilometres long. It takes the same sort of effort. We're also in the process of trying to automate that workflow. I'm going to finish up with a couple of what-ifs, if you like. Last year it dawned on me, and this is, and I'm not sure how many people are here in the infrastructure space, but in the last year and moving on, 5 different software houses have been developing parametric tools for bridges. You've got Tekla, you've got Sophistic and Revit, you've got Bentley, you've got Katia, got their own bridge tool, and you've got Allplan. Allplan is the same maker of the company ArchiCAD. They also got Celebri and Bluebeam. So these are all very powerful people in the industry, all exploring use of parametric tools and whatever. So you can kind of get a sense if they think that there's a need, or you kind of get a sense of where they're thinking and what they're doing. I get a bit wary when people say they can write one tool and they'll do every bridge and every combination and whatever. I always found that it's at the margins where things different. Yes, you can use a script to get you 80, 90%, but it's the devil's in the detail. And that, I'm not sure that there's a one-size-fits-all approach, but we'll see how it goes. But that just gives you food for thought about what people are thinking, and there's other people playing in this space. What are the opportunities that we're exploring at the moment? Connected models. So we've done a lot of work with Tekla, but what if we were able to automate the connections? So, and that's one thing we're exploring at the moment, and this has been done on a few projects. This was some images of the new stadium up at Townsville, the new rugby league stadium, which has just been opened in Townsville. 3D reinforcement. It's the holy grail for me. I know it's not very exciting for most people. Steelwork models we've been doing forever and a day. Reinforcement models, huge opportunity. Again, I should get a slide of the drawings for these and then compare the drawing to the model, and I think you'll get it. Again, I'll go back to if a picture tells 1,000 words, how much data does a model do? The beauty of these things is you can treat them like a component. We can use the parametric tools to place them. All of a sudden, we can do a bridge, do a lot of options. It's very, very powerful stuff. This is an example of one of the rail bridges we've done where we modelled all the reinforcement. This is some work being done by Joseph Tang in Brisbane office for ProBuild, where they did 3D reinforcement model for I think it's a 1.5 metre deep transfer floor on a tower in Brisbane. Very successful. Telling he's dreaming. I've been working with drawings, as I said, for 40 years. If I could get rid of them tomorrow, I would. I've got a colleague, and he and I shared a similar drawing, and his lament is, John, why do we keep using the latest, greatest tools and then dumb it right down to make it look like it was on the drawing board? I go, yeah, I'll share your pain. So, I'm going to talk about this project. Can we deliver without drawings? Well, we have, and we've done many examples of this. But this was the travellers' sculptures on the Queen's Bridge down at South Bank, done in 2004. was schemed by an artist, provided us with a CAD file. Obviously the fee for this sort of project is not that large. Can you do drawings for each of those sculptures? Yeah, maybe. Would it cost you time and effort? Yeah, it did. So we talked to the fabricator, we got a programmer in. We asked them what data they needed to fabricate it. They said, we just need an Excel file. So we had a programmer take the CAD file, rationalise the geometry to a series of arcs, then write that geometry, do the analysis tools, and then write that geometry to an Excel file, and then gave that to a fabricator. And lo and behold, they're up. Really happy with our outcome. Quite disappointed that that was done 16 years ago, and we're still, it's not business as usual. Per stadium, I'm not going to talk in detail about per stadium, but we developed a Tekla model for this project from scheme design all the way through to detailed design through to construction. We talked to the shop detailer who are also using Tekla. We talked to them about how can we make it easier for you. This was fast-tracked, so the west quadrant was delivered before the east quadrant and the south quadrant, etc., like most big projects. We also started shop drawings before the design was finished, before the mechanical penetrations were known, before the architecture was finished, even before the structure was finished. Classic large project. We talked to the fabricator or the shop detailer and said, how can we make it easier for you when we issue you a new model? So they said, can you add attributes in your model that tell us what's changed and add that granular level of detail? So basically, because we were using the same tool they would, because we embedded data in our model, every time we handed a model to them, they could run filters in their model, and they could tell what changed, what was new, what was added, what was deleted, and whether the size changed or shear studs or whatever it was. It basically made the drawings irrelevant, and that's the key message that I took out of this project. It made drawings irrelevant. Yes, we delivered drawings because that's a contractual thing, but the fabricator, the shop detailer, did not use it. Then I'm going to go to a what if. This is a bridge project that's just being erected in Sydney as we speak. I'm not going to go into detail about this project, but it was done grasshopper analysis to a Revit model for documentation. But the key message for this was they went to fabrication, grasshopper, IFC to the fabricator. So just think about that. You don't need to go to any other tool. You can go from IFC to a fabricator. There's other examples you'll find where you can go, okay, we're taking out some of those other tools in the picture. So what are those opportunities that allow us as we go forward? I'm going to head over to Rhys, who's going to tell you about what they're doing now, and then Josh is going to talk about a bit about the future. Thank you.
So, John, sorry before you go away. So we have time for a few questions if someone has a quick question from John. Anyone? Yep.
From I just got the questions. You mentioned a couple of times now we're still tracing up some things that we've done probably 10 years ago. What's you sort of look at why is industry so slow to catching up to some of the technology already been for a long time?
That's a good question. I think the processes we're using today are similar to what we used before. We're just using different tools. It's a little bit frustrating. I find it a little bit frustrating that we're still trying to... I still meet people and they go, we don't need a model. Or, we don't need to do this. We just go back to the drawing board or, look at the cathedrals and the pyramids. We don't need this stuff. So I think there's human nature. There's a lot of people resistant to change. I do think the software houses have a lot to answer for. I think there's a lot in the industry that are, if you've invested in a certain software, you tend to not look outside that. I don't want to bag Autodesk publicly, but I could, every one of those projects that I showed you, if I waited for Autodesk to release a product to do them, I couldn't have done them. Every single one of them. That's just fact. Autodesk are consistently 8 to 10 years behind the industry. So if you think that they're ahead of the game, I think you're kidding yourself. But it's mostly people. You know, we get people rolling. You get new people rolling in through the door. They come with different skills. You know, where our experiences. You know, I've been around a long time, so I've seen a lot. But you know, we only know what we're exposed to, if in a sense. It is a little bit frustrating that it's not business as usual on every project. I've got to say that. But you know, I'm kind of hoping. I see a lot of, especially in infrastructure and buildings, I'm seeing a lot of examples now where people are starting to get it. I really do. But I come back to, I'm quite pragmatic. I'm just a cog in the wheel as a structural technician. I work with the engineers and the architects to deliver a model or data to give it to a fabricator. I did shop drawings when I first started before I joined Arup, and I think that served me well because that's been my mindset ever since. If I was to do this job, what information would I need? That's how I approach it. And these tools, these digital tools, they are just that. They are a tool to help you deliver a job. So I just strongly encourage people to play around with it. Don't take my opinion on whether Autodesk or one tool is better than another. Play around with each one and make up your own mind. That is what I would encourage you to do. And use your projects. Don't wait for that rainy day, really, seriously. Every project is an opportunity to explore. So, does that?
Yeah. We just, because I got a sort of 100% problem where it's very difficult to get people to turn around to embrace using technology, which would save more time.
It is, but you know, and the hardest thing, and I get it, the hardest thing is to go to someone and go, Joe, can you do this for me? I need it done by Friday, but I want you to use this new tool. What happens? Joe falls back on how he knows he can deliver by Friday. So it's up to businesses, it's up to the organisation to create an environment where Joe can take a risk and maybe not meet Friday. Because we all know, and hopefully these projects, every one of those projects, that was the first time we used those tools. Every single one. And that's not small projects, right? So talk about taking a risk.
I find it's sort of the bigger project tend to take on the more latest tool. The small project tend to be more conservative.
I get that. Same with us. I'm not so sure because there's a lot of people go, this is a big job, we could go really badly. So let's, you know, our losses could be huge, whereas a small project, your losses aren't so small. I think it's more the environment, and it's up to the leaders. I get frustrated. So we've got some grads coming in, and we had some senior people sit them down and go, we're going to teach you AutoCAD or MicroStation. It's like, oh, we're not going there. We're not teaching them that. We're going straight to Grasshopper and Tekla. Right? So why do we, as a business, get really clever people, digital natives, for want of a better word, bring them into an office and then go, oh, no, don't use those new tools. Use this tool that's from the 70s and 80s because that's all I know how to use. Right? But to push back against, you're a grad, you're coming in the door, how do you push back against that? It's bloody hard. Yep.
Sorry, this question and answers went longer than expected. So we got a couple more presentations tonight as well. But I think, John, if you stay with us after the presentations, we can
do questions and answers.
After the presentation. So we go to our next presenters, Rhys. Yes.
Alrighty. All right, thanks for coming here, guys. Thanks for choosing to come here over Melbourne. If you don't know what Melbourne is, it's a conference similar to this, but across the whole BIM space, digital twin, and all that cool stuff. If you didn't realize Melbourne was on tonight, there's probably still time, like after this, you know, to head down for some more free beers down there. But anyway, so a little bit about me. I've been here for a bit over 6 years. I was actually originally hired by Mr. John Legge right here. So I was web modeling and studying for about 4 years. I'm now a structural engineer and very interested, and I've definitely been encouraged over the years to explore different methodologies to deliver our projects, similar to what John's been talking about. So this is sort of a case study of a workflow that we set up recently for a project. It's a underground concrete structure. So we're trying to integrate a whole bunch of external inputs into a central database or central model to produce analysis models, but also design models, and then also try to generate 3D reinforcement out of that same data. So essentially, we start out with a whole bunch of tools that we think we'll probably use, and we want to decide on like the process we're going to use to generate ultimately our Tekla structure model without 3D reinforcement. Our Rhino model is going to end up looking like this, essentially, something like this. But the reason why we'd use Rhino is because for geometry operations, it's probably the simplest, most refined. It also has a lot of the parametric modeling that John's been talking about inbuilt into it with Grasshopper. And yeah, you can also do geometric calculations quite simply within Rhino. So we'd be analyzing using GSA. One difference here is that we're aiming not to be doing any hard coding of parameters or any modeling essentially in GSA itself. We're trying to set up our entire model outside of GSA, but also within our Rhino model, we're defining parameters that GSA isn't interested in, such as lap locations if you're talking about reinforcement. Cover, like GSA isn't particularly interested in these parameters, but we're defining those in the initial Rhino model to use later on. We were using Excel as our design tool, so what's doing the maths behind our code checks. Excel probably isn't the most ideal solution, but we have like existing skills in Excel, existing tools, so existing spreadsheets. So we sort of tried to work that into the workflow. And ultimately, we're delivering our design documentation in Tekla. Yeah, so essentially trying to generate a 3D model of our reinforcement. Unfortunately, yeah, we are delivering drawings at the end of the day, but if we have our 3D model, we can hopefully use that to, interrogate, hopefully for, additional purposes in the future. So we've got all our tools that we're pretty sure we're going to be using, but before we actually start out setting up this workflow, we want to actually map out how we're going to use each of these tools. And it's probably more about the linking between the tools. So we end up with a workflow that looks something like this. That's at its heart, this whole workflow is sort of revolving around Speckle, which is sort of an interoperability tool in our case. So this is sort of a summary of what we're going to be doing. So analysis and design driven by a Rhino model, avoiding manipulation in GSA, sending our analysis results back into Speckle, and then reading it into Grasshopper to send to Tekla to generate a 3D reinforcement. So here's a couple of videos. some of this workflow in action. We've got our Rhino model, we're sending it into GSA, hitting go. Once it gets into GSA, we're not doing any manipulation within the GSA environment. We're sending the results out of GSA back into Speckle. We're sending that to an Excel spreadsheet, which is doing our design, and then we're sending the results of that design back into Speckle, and then into Grasshopper to generate our Tekla model from the Tekla Live Link, which is ultimately what generates our drawings at the end of the day. So another advantage of using Rhino and Grasshopper is that we can actually visualize some of the inputs. So this is a bit of a lesson learned, where you've got a huge amount of data coming into the model. You need to interrogate that data, and sometimes the software tools that you're using are a bit challenging, or the options of visualization of that data is pretty tricky within those programs. It's not always super flexible, so Grasshopper is actually a really good visualization tool at the same time, so you can actually be visualizing your input data and checking it before you're even generating it in your analysis model. So here I'm visualizing some earth pressures that are on this underground concrete structure. And then you can also do things like label the actual values, label how deep underground you are, which is quite helpful. So I've mentioned Speckle a few times. So what is Speckle? I think it's essentially a database, but it's also the link between programs. So this is how they describe it. So it's a method of moving data between your different platforms. So in a quick, manageable way. So you set up streams, you're sending essentially the important data between programs. You're not trying to send the whole model at once. But essentially you could send a stream with all of your data, and then get the program at the end of the day to interrogate that data and only pay attention to the relevant data. That's essentially how I would describe it. But it sort of relies on these links. So this is the GitHub page of Speckle. So these are existing links that have been developed or are in development. So Speckle itself is in pretty early stages. You're not going to be able to do everything immediately in Speckle, I would say, that you need to do. But the advantage is that it's open source. So you can actually download the whole code base of GitHub and start making code changes yourself if you have any sort of programming experience, or if you want to learn a bit of programming. So this is a way people can start fixing bugs themselves. They're not relying on outside software development parties to fix their problems for them. Or alternatively, companies could start hiring programmers, for example, to start doing some of this development for the end user. So I managed myself to get one commit. So I actually had one little change that I made to the code integrated into the overall Speckle structures code, which I was pretty happy about. I think I made like 2 characters change. It's just a little bit of a bug, but I'm still happy about it. Another advantage of Speckle is that it's decentralized. It's open source again, so essentially any company can set up a new server. They're not limited by licenses. You can do it completely offline, within an intranet if you want to. And the data on the streams is completely flexible. It's all just JSON format, so it's not really a limit on how you're sending data. I guess at the end of the day, companies like Amazon are probably doing quite well because they end up setting up the servers for you if you're working at a company. So we had our workflow diagram up before. So what sort of improvements are we thinking about making in the short term? Maybe instead of Excel, we could be swapping out Excel for C# or Python. So using a more code-based language to do our design checks. Could also be swapping out our analysis programs. Not everyone's using GSA. Right now, Speckle, we've been helping develop it for GSA, but ideally, you're not locked into one particular software at all. You're able to swap out, say, we don't want to do our documentation in Tekla, let's send it directly into Revit or vice versa. I don't want to be modeling in Rhino, so I want to do my design strips in Revit. Essentially, it's just geometry at the end of the day in these cases. But essentially, ideally, you're developing links. All of these arrows are the connectors for Speckle, and I think eventually, I think big picture, this is what we're aiming for. Like, a sort of plug-and-play environment where you're able to have flexibility in your workflow. And that's it for me. That was quick.
So we'll leave the questions for the end of the next presentation, which is Josh. Josh is a structural engineer working in Arup's building structure group, and his talk focuses on the future trends of computational design in the AEC industry. Thank you, Josh.
Hi, everybody. As I was just introduced, I'm Josh. I'm a structural engineer in the Melbourne Buildings team, and I'm also one of the digital integrators for the team. John Legge has talked to you just now about the history of computational design in Melbourne. Rhys has touched on some of the current areas we're exploring in computational design, and I'm going to drivel on for 5 to 10 minutes about where we think the future might be in computational design. So you're going to get a bit of a theme of audience participation in this. Can anybody tell me who or what that is? Don't be shy. The Grim Reaper? Yeah, fair guess. Actually, that is the Ghost of Christmas Yet to Come. But it bears a striking resemblance to the Grim Reaper, I agree. I didn't put this in to be a portent of doom. The thing I kind of wanted to communicate here was, in A Christmas Carol, the future was represented by something that was faceless, it was voiceless, it was intimidating because it was anonymous, right? And that's what the future is. It's something that's inherently unknowable. And so I think what I'm going to do is to frame this whole presentation in light of the fact that we really don't know what's going to be happening in the future. There's going to be a whole bunch of disruptions, and it's anybody's guess as to what those things might be. Now, keeping that in mind, what do we think the future might hold? I put a whole bunch of buzzwords, as Rhys called them, on this slide just to prompt thoughts, conversation, and maybe some discussion afterwards. These are some of the things I think people tend to think of when they think of the future of the AEC, so there's lots of sort of sexy things in there, right? There's a robot climbing stairs at a construction site and taking some photos. There's a drone flying over a construction site, and a machine learning algorithm is being used to identify construction equipment versus just normal cars. And I think the thing that really affects us as computational designers are the others, which are digital fabrication. So we've got freedom to design stuff that we couldn't design previously, or potentially couldn't have been built previously. And we can also visualize design in different ways, as both John and Rhys have talked about. So you can see in the middle right image there, the digital twin being held up to a construction site to show a design in progress. Now those are kind of like the sexy, nice, sparkly, shiny things that we think of when we think about the future. But those things are perennially 5 to 10 years away, right? I think the things that we're going to be faced with probably within the next 5 years are a little less shiny and a little less cool than that, but I think they probably will affect our industry in just as a profound way. And so one of the first things I'm going to touch on in that regard is something that John Legge has already been talking about. It's models as a deliverable. Alrighty, second piece of audience participation. Hands up, everybody who considers themselves an honest person. Jesus Christ, a pack of liars in the room. Check your wallet before you leave. No, I think you probably all consider yourself an honest person, right? And what is an honest person? An honest person is someone who likes the truth. And in our industry today, that makes us all very lucky because there are so many sources of truth, right? Take your pick. You've got the Revit model, you've got the latest IFC model, you've got the PDFs that have recently been updated on Aconex, or you've got that crappy little hand sketch that you did down at the contractor's office last week and lost on the way back to the pub. Yeah? And all of those are probably going to contradict each other, all of those are going to give a different version or flavour of the truth, none of which are probably going to be quite right. And that just contributes to this mess of data fragmentation that we're all experiencing in the industry at the moment. Now, I think that it is inevitable that with time we default towards the 3D model. We're able to communicate so much more than we previously did. John Legge, his eloquent way, stole a phrase that I was going to use. If a picture's worth 1,000 words, a model's probably worth 1,000 pictures, right? We can communicate things in 3D that it's nigh impossible to communicate with in 2D images. And so until we completely transition, I think this data fragmentation is something that's going to plague us in that transitional period. But as John has given some examples of, we are working towards that, and you can see examples of workflows on different projects we have delivered where the model is king. So I know the Cox guys frequently work with us on Grasshopper scripts that are used to deliver some really big projects, right? We collaborate on the one set of truth, the one piece of data that defines the geometry that everybody uses. But I wanted to communicate that that's not only applicable to large mega projects, it's any project where the geometry can be easily communicated through a mathematical definition. And so I've thrown in here just a small job we worked on in Queensland, which was the Florence Street Arbours. A little bit of computational geometry defined in a Grasshopper script, but again collaborated on between the architects and the engineers. Other examples where we're finding that the model has to be used, we basically have no choice in communicating design intent. These are some of the connections on ACU. I dropped these renders in for a couple of reasons. One, they look nice, but the other reason is to communicate the fact that these are probably some of the more simple connections we have on that building. Some of the connections are unbelievably complicated. And when we decided to finally bite the bullet and document this, we knew that documenting in 2D just wasn't going to cut it. And so we actually ended up communicating some of the designs to the fabricator in 3D. So this is an IFC model. It's actually embedded in the PowerPoint and would give me a really nice effect if it would just kindly spin around. I don't think it's going to. But this is one of the fully welded truss nodes that we had for ACU. This isn't even the most complicated one. This is a fairly standard one. But again, the nature of the stiffening required on a joint like this, just too difficult to communicate with a set of 2D drawings. We really defaulted to the IFC model. And the IFC communicated this so efficiently, and it took a couple of hours to prepare as opposed to the drawings, which would have probably taken days. I'm throwing this one in here, and I'm looking at Clayton wherever he is in the room. This one's kind of being held up as a bit of a poster boy project at the moment. I wouldn't say we were showing off, but it was testing our digital capability. I think that's probably a fair description. So this was an exhibition held in the Arts and Science Museum of Singapore. John Legge showed you some beautiful images of that structure just before. It was done in collaboration with a group called Foria, who are experts in the AR/VR space, and they prepared this amazing state-of-the-art presentation, which was an augmented reality experience for the attendees. Now, Arup delivered a structural design and the acoustics design for this project, and we, I'm not sure if it's going to play or not. No, it doesn't look like the video is going to play. We actually scanned a 3D point cloud of the exhibition space that we were preparing the stage for. So we had a 3D model of the exhibition space that we were going to be placing this platform and this exhibition inside. And then we used parametric modelling and algorithmic design to prepare several different options and situate them within that 3D point cloud model to communicate what those would feel like in the actual exhibition space to the designers of the experience. When that wasn't enough, we 3D printed scale models of some of the options, and those 3D printed models were actually constructible models, so the designers at Fourier could actually put the stage together themselves and see what it would look like and how it would all connect. And then we did a 4D modelling sequence showing how we intended the contractors on the actual day of construction to put the thing together. If this would play, this would be a really nice graphic of that. But as the final part of that, the structure itself was a fully CNC platform, and the final deliverable was actually a piece of G code. I'll see if this will play. It was a plywood structure. It was really, really beautiful. But again, absolutely no drawings as the final deliverable. It was all done through a model direct fabrication, exactly like John Legge has discussed before. So I've talked about some of the cool stuff we can do and some of like the stuff we get excited about, right? But what are going to be some of the disruptions in the years to come? And I think one of the biggest ones is probably going to be the Uber effect. Audience participation coming up. Who here has worked on a project where their company or another company involved in the project had some of the drafting or modelling outsourced to a different country? Yeah, most of you. We're seeing it more and more, right? And that's because it's super easy, super convenient for people to access, to locate, to find those services, right? It's the Uberization effect. Every industry is experiencing it. This was a graphic that I downloaded from a Twitter page that I Googled yesterday morning, and that is a screenshot of a web page for a company called Hello Artisan. And the service that they offer is actually sourcing contractors to deliver renovation works for different houses, whether they be electrical, plumbing, painting, or even structural. Now, this is small scale, but depending on the nature of the subcontractor work that different projects have, I don't see why this couldn't scale a bit more. I don't see why we might not witness this effect on larger scale projects. And so, from a computational designer point of view, what might that mean? Well, our job is already complicated. It gets more complicated when people are working in different time zones, and so you don't have people occupying the same hours of work. You have different conventions for data in different countries, potentially different software packages. You might have additional constraints added by a language barrier, and the entire process of design becomes more complicated, and we wind up in this miasmic cloud of design hell. I think that as we move forward, it's inevitable that all of us need to be more versed in not just our core job. I think that one of the final thoughts that I'll leave you with is that we're not just going to be an architect or a structural engineer or a contractor moving forward. We're also going to have to adopt roles of data scientists, of programmers, of modelers and technicians and drafters, and people who are versed in 15 different pieces of software. And that is going to make computational designers probably in 5 to 10 years' time completely different from computational designers today, which means that, as John Legge has already indicated, people are fundamental to what the future holds for computational design in the AEC. I think it's time for a beer if people are keen.
Thank you, Josh. Thanks very much. So we just have to leave the building at 8. So we have a little time for beer. So if you want to grab yours, be quick. And also, some of us are catching up after 8 at the bar downstairs called Bar Nacional. So if you want to have a chat and continue drinking, we'll see you there. Thank you, everyone. Thanks for attending.